Hello, grade 11s. Welcome back to another online lesson. So today, hopefully, the video quality is a little bit better. The files are going to be a little bit larger and longer. It'll take longer to export, but hopefully you guys are seeing a screen that maybe looks a little bit clearer. Today, what we're going to be doing is we're going to be talking about stationary points. And the goal today is to be able to find these stationary points and classify them. So stationary points come in different types. They're just points. They're special kinds of points. They're points that satisfy certain kinds of properties. And there's more than one kind. And so today we not only have to find them, but we also have to be able to classify them. Okay, so let's get into it. We say that there's a stationary point at x equals a if and only if the derivative at x equals a is equal to 0. So stationary points then are points where the derivative or the slope of the curve is exactly equal to 0. And we've seen these kinds of points before, but we haven't given them a name. So for example, if you look at this curve kind of, is increasing here, going back to last class's topic, and then decreasing. And then right at the point here, you can see that the slope of the curve is 0, and so here we have a stationary point. And then similarly, right down here, we also have a stationary point. And then this curve's kind of interesting. Here we have a stationary point right here. The slope of the curve is 0. So let's go over these stationary points. I just want to make it clear all three of these are stationary points. So this thing here is a stationary point. I'll abbreviate it with SP. Okay, so that's a stationary point. And then this is also a stationary point. Now, there are different kinds of stationary points. I'll label them here. There are exactly 3 kinds. So a stationary point can either be a local maximum, and that's the first kind that I'm going to show you. A local maximum satisfies certain properties. Number 1, at the stationary point, of course, the derivative has to be 0. That's what it means to be a stationary point. But for it to be a local maximum stationary point, the function has to be increasing to the left of the stationary point and then decreasing to the right of the stationary point. Now, at the stationary point, the function's kind of changing from increasing to decreasing, but to the left and to the right, it needs to meet those conditions. Okay, and the conditions are that to the left of the stationary point, I'm going to just drop the x coordinate of this stationary point down. So let's say that this stationary point here is at x equals a. What we want is the derivative to be equal to 0 exactly when x is equal to a. And to the left of x equals a, we want the derivative to be positive. To the right of x equals a, we want the derivative to be negative. Okay, and what that translates to, remember from last class, if the derivative is positive, the function's increasing. And then right at the stationary point, it kind of switches from increasing to decreasing, and the derivative also changes sign. So if the derivative is 0 at some x equals a, and the derivative sign changes from positive to negative, we have a stationary point, but also we have what's called a local maximum. Okay, so this stationary point is a local maximum. We'll abbreviate that to just be a local max. The word local here just means that in the locality of this stationary point, you can kind of imagine drawing like a tiny box. Like if we draw in this tiny box here, if you imagine looking at the y values of the curve very, very close to the stationary point, the y values are they're dropping off away from the stationary point, or in other words, the stationary point has the highest y value in close to the stationary point. The stationary point has the maximum y value. So we would say in the locality of the stationary point, close to the stationary point has the maximum y value. And so we call it a local max. The word locality is kind of very similar to the word locality in English. Like, for example, we are in the locality of Taichung. If Taichung's the city and Taiwan is the country, Taichung is the locality. And in the same way, locality here refers to, if we're close to the stationary point, the y values of the stationary point are the largest they will be in that locality. In a similar way, here, down here, if we look in the locality of the stationary point, so if we look around it, we can see that in the locality, the stationary point is the lowest, or the y values of the stationary point are a minimum. So we call that a local minimum. So I'm going to drop that down here. Let's say that this local minimum occurs at some x equals a. And let's suppose then that the derivative here, you can see that to the left of the stationary point, the function is decreasing. So the derivative will be negative. And then to the right of the stationary point, the function is increasing. So the derivative will be positive. So here, the derivative is changing sign from negative, and then to 0, and then to positive. And because of that, we call this a local minimum. Okay, so that's a little bit unclear. Let me just write that. So this stationary point is an example of a local minimum stationary point. The last stationary point is a little bit different from the other two. So here you have kind of a special scenario where the function to the left of the stationary point is increasing, increasing, increasing. And then right at this point, we can maybe say the function is stationary for just a moment. And then it's increasing, increasing, increasing again. So here, it's not a case where the derivative changes sign. The derivative sign remains either positive and maybe 0 here, but it remains positive elsewhere. So here you have a special kind of stationary point. This stationary point is called a stationary inflection. Inflection you'll see spelled with an X, and then sometimes it's also spelled with like a C, like inflection, but how you spell it doesn't really matter. It's called a stationary inflection, or in long form you'd call it a stationary point of inflection. Okay, so let's label this one. This one here is a stationary inflection. It is a stationary point, but more specifically, it's a stationary inflection. So again, let's drop down the x coordinate here. Let's say that the stationary inflection occurs at some x equals a. And let's try and determine what the first derivative's sign will look like. To the left of the stationary point, derivative is positive. At the stationary point, it's 0. And to the right, it remains positive still. So we're going to have positive, 0, and then positive. Okay, so you can also have a stationary point that goes in the opposite direction, or faces it is kind of the opposite stationary inflection. It maybe decreases, is stationary, and then continues to decrease. And that would also be a stationary inflection. So hopefully you can kind of see that you have 3 main kinds of stationary points: local maximums, local minimums, and then stationary inflections. And a stationary point is defined by this property, that the derivative at the x coordinate of the stationary point will be 0.